I think I'm live now. Hello, everyone. Um, yeah, I did a mistake again. I thought I went live, but I actually didn't. Um, but yeah, hopefully everyone is doing well. I'm not even sure how long this stream will be. Most likely like about 3 hours maybe. Uh, Maybe I'll do some break in between, just so I can like rest a little bit maybe. I don't know. Or maybe I'll just stop um, after a while. Hello, James Grind, welcome. Oh, by the way, I haven't made you mod. Let's do that. Add monitor, managing standard. Add match. All right, now you should have a nice and blue name. By the way, I should probably. I mean, it's not really. I don't really need mods now. That's for the future. Um, we'll join during breakfast and get work later. All right, nice. Yeah, I have no lectures today, so yeah, I'll be doing a very like streaming all day basically. Hello Toro, good morning. Hello. All right. Well, I don't know if more people will join, but I guess it doesn't really matter. We'll just begin. We'll just get to the good stuff. I wanted to make this like a very nice stream setup and stuff, but honestly, I don't know if I even bother. I don't think it's that important. I mean, you could have like nice layouts and stuff, but yeah, it takes way too much time, and I'm not sure if I really bother that much and care that much about it. I don't think it matters that much with the stream and stuff, you know. So maybe a tad bit. Um, I mean, if someone offers to do it for me, and where I have to pay like a little money, I would. But I can't bother doing it myself. I'm doing math right now too. Noise. But basically, what we're doing today, I want to repeat some of the. So the title is called Counting and Length, and I totally stole it from this chapter. Hopefully you can see it. Um, it's chapter 3 of my. I'm not sure really what you would call this course. It's called Introductory to Higher Analysis course. But it's about counting and length and how you count sets that are infinitely long. Slowly make it better if there's anything people suggest. Yeah, that would be nice. Yeah, I guess like yeah, something needs to be improved. Yeah, you guys could write it down maybe. Um, but yeah. So how do we count infinite sets? That's I guess the main topic, right? And by the way, my goal is to go through the entire. This is a 9-page PDF. Already done. I've already like skimmed through a little bit. I want to do all the exercises, but I'm not sure if I will be able to do it. If I need some help, I'll just ask ChatGPT. Um, and yeah, we'll just get through some questions today, I think. Um, there's some Lebesgue measure as well, which is kind of daunting. Uh, but yeah. I'm doing sets too. Noise. What type? What are you doing with sets? Is it like set theory or what? Um, but we had a seminar like a couple days ago. I think Monday, right? Um, about this kind of thing, and yeah, I guess maybe I want to go through a little bit because I feel um, kind of that I need to repeat some things. Maybe if I have 1.1 here, the first one, we have an infinite union of um, of countable sets. So I guess maybe one would go through what a countable set is first, right? But it's yeah, I'm not sure if I want to go through it super detailed right now. I'm not sure exactly how detailed I'll be with these streams, but I guess if a set is countable, there is a bijective map with that maps natural numbers to each element of the set. I'm pretty sure. So I guess yeah, this question just wants us to. It's a very standard standard way of. I think here's the hint that we need to. It's use the same argument that was used in the lecture notes to prove that the rational numbers is countable. So I think in this case you would do like. So you would. I think you would. Yeah. Right. So you have the first. If you have A1 here, and this is some countable. I'm not sure if you can see this. Yes, you can. If this is some countable set, which we denote its element by this, I guess. I guess yeah, we can lay out all these guys. Wait, let me just think. Right. So yeah, I think yeah. So you would have a I guess this would be a natural number line, right? I'm not sure if I've ever done this like this. But if you have elements like this, and if this row is A1, and this row, maybe one would do A2, and then A3 here maybe. And then, let's see here. I guess you wouldn't do the negative ones, right? You would do 2, wait, 1, 2, like this. Hopefully that's visible to everyone. I'm not sure if this is too small. I just started with the basics this year. Noise. I'm guessing with operations and stuff. Set operations. Very nice. Maybe we can zoom in. Maybe not. Alright. But I guess, yeah, you could just number all the sets like this, or all the elements. I'm not gonna write everything down, but anyways, I think, yeah, the argument would be that you can then, yeah, you can, wait, how do I do it? It would be something like this. So you can hit all the elements by having like this kind of map. So yeah. Yes, very nice. Cool. Probably I'm the the worst guy to explain this kind of stuff. And the same is, or I guess a similar argument for B would be the case. Yeah, for proving that R is irrational or not countable, you would do the same with the set Bn. Let's see here. Is this Unimath? Yeah, it is. It is. All right. So that. All right. I think this 1.2 is pretty interesting. Because it has a lot of connections with the Cantor set that we will do later. Let's see here. I'm in 11th, so yeah. I mean, certainly this is nothing you would do in high school, or at least that's definitely not what I did. So, I mean, it's definitely not worrying if if this goes over your head, you know. To be fair, this is also very complicated for me, or I guess very confusing. Okay, man. I don't think I need to go through this. Yeah, I think so too. Yeah, we can begin with this. With this these lecture notes. Right. If there exists a bijective function, so the definition of cardinality. Right. I'm just studying side by side, trying to understand a few too. Cool. Cool. Alright, so I think these examples is just to get you familiar with the notation. I think, yeah, can be maybe confusing, like the definition of cardinality. For continue the count with 1, 2, 3, and so on each time you hit a new integer. Right. Cool. Right, and this is the argument here in this picture I try to do with the problem on in the seminar. And yeah, it's just finding a way to I mean, it's a very visual argument, but I guess that's enough in this case. Yeah, I guess so. I guess you don't have to like formally write it down very explicitly. You can get a gist of it. I guess this is not the most rigorous kind of textbook, right? This graphical way of counting is super cool. yeah, it's interesting. I think he mentioned as well that this is not the most rigorous, but it gets the point across, I guess. 0 divided by 1. We count 0, next we move our finger to record at 1, 1, which is here. Finding the rational number 1 divided by 1, counting 1. Yeah. Ignoring duplicates. This argument is visual and not completely formalized. Yeah, it should convince you that there is a way to count rational numbers 1 by 1. So none of them are missed. Yes. Each element will appear in exactly once. This tells us we can write the rational numbers as a sequence. Yeah, I guess this step is also very logical, right? All this seems connected though, like not completely different. Yeah, I mean, yeah, I'm not exactly sure what you're doing, but yeah, this is certainly a lot in like set theory, or I think so at least. I've never really studied set theory that rigorously, to be fair. So. Alright, this is where it becomes a bit interesting. We call A countable if there exists a bijective map. We call A uncountable if there does not exist any f from the natural numbers to the set A that is onto. Alright. Well, that's... Wait, let's see here. Definition 3.5 can be formalized in a more general language. Indeed, cardinality can be defined as follows. For sets A, B, we say that if there exists a one-to-one map function from F to B, kernel of A, kernel of B, if there exists a bijective, show that cardinality of A is less than cardinality of B if there exists an onto function. Right. Well, this is... Oh, okay. Okay, I think there's some subtlety because I was kind of confused, like, because this is F from the naturals to A, and this is F from the set B to A. Feels a bit more like number theory for now. Relations and functions, like the one with the Cartesian products and stuff. Yeah. Oh, it's cool that you're doing relations and functions. Relations is like, yeah. As I know, it is like very algebra. It's used very much in like abstract algebra and stuff, which I will do, like, I don't know, maybe during the weekend today, or this week. But a Cartesian product is very nice. I don't really know like number theory. I mean, maybe I don't really know a lot about it, but I guess. I mean, for our project we're doing, we're like constructing because there are many different ways of constructing the real numbers, and it feels like it's number theory, but I'm not exactly sure, to be fair. Okay. Alright, so it's uncountable. This is fairly okay. If there does not exist an F from natural to A, but what if it does? There does exist from natural to A. Um, yeah, this is, I'm not even sure if I understand this definition. Like, what if there does exist an onto function? What do we call it then? What if there is an onto function that is not one-to-one? Okay, well, if it's not one-to-one, then we call it finite, right? I guess so, right? I guess that makes sense. Like, if it's not bijective, it's either not onto or not one-to-one. So if it's not countable, it's either uncountable or it's finite. So if it's finite, there is an onto map. This is kind of weird. So we can have a finite map that is not countable. Or no? Yeah, makes sense. Does one-to-one equal bijective? No, it like one-to-one is like bijective is, I don't know if you can say equal here, but it implies one-to-one and onto, like this. So I'm guessing like if A is countable. So if you have a set A that has some elements, A1, A2, there can exist a bijective map from natural to N to A. So yeah, then it's countable. Finite not countable, like infinity. Yeah, it's weird. Like if it's not okay, so if it's not on one-to-one, it's finite. But aren't all finite sets countable? I guess we can make it countable. So maybe I'll ask ChatGPT for this, honestly. I mean, I'm guessing like if it's one-to-one, like usually we can restrict the codomain, like to make it onto as well. Yeah, maybe I'll ask ChatGPT. This is a prime moment to wait. Let me just do this. I don't have ChatGPT open. So if A does not have a one-to-one function, it is called finite. Doesn't this imply that f is also countable? Does this intuition, is this intuition correct in this definition? Maybe I'll put it up here. Are you doing functions? It low-key makes sense in a weird way. Please explain. I need your knowledge, Jemima. How am I doing? I'm doing it's a chapter on cardinality and length as well. But we'll get into length later. I just want to try to understand these definitions first. I think that's very important. I need some wisdom from ChatGPT. All right. A is called countable if there exists a bijective f. Yes. In many texts, this is called countably infinite, i.e. some same cardinality as n. Nice. Okay, if there does not exist an onto map, meaning that we can count. Okay. Feels like I'm brain farting here. But yeah, so if there does not exist an onto map, what does that mean? If there does exist an onto map, we have that. Yeah, I see. All elements in A. Yeah. So all elements A have at least one partner in the natural numbers, right? If there does not exist an onto map, some elements in A may not have a partner in N. I think this is it. I guess kind of forgot the definitions, right? If it's an injective map, right? It's called finite if there does not exist an injective map. Okay, so if it does not exist an injective map, we have that one of n may be right. So yeah, right. Yeah, so one natural number could be mapped to many. Okay, let's read your answer, Jemima. Like if bijective is then considered countable, then just onto would be uncountable. It includes many types of relations that can be one to one or many one. Right. I mean, for me, I think if it's like not onto, we cannot guarantee that all the elements in A has a natural number partner, right? And if it's not, I feel like I need a definition of one-to-one, honestly. Jesus Christ. Because if it's one-to-one, I mean, I guess the normal definition would be that, right, there are no, for element in A, there are not two partners in the natural numbers. So if it's not one-to-one, And if it is restricted to one-to-one functions, we call it finite. I think so. I'm not quite sure about my reasoning yet. It's defined from n to a, right? Yeah, it is. Yeah. So the function is from n to a. Yeah, this is the definition where I'm struggling with. If it is either finite or countably infinite. No injection from n to a. This means that the set of kernel of A is less than kernel of n. Or finite sets also normally called countable. I guess this is what we're tasked to show in the later problems, like exercise, the optional exercise. Wait, let me just think. Do-do-do-do. Could there not be a one-to-one? I guess it can. Yeah, I'm not sure. Maybe we'll just move on. Definition 3.5 can be formulated in a more general language. Indeed, cardinality can be defined as follows. For sets A and B, we have that cardinality is less than cardinal of B if there exists a one-to-one function f to A, f to B, or f A to B. And they're equal if this is the case. Show that cardinality of A if there exists an onto function. This seems very difficult, honestly. So I need to show that 3.1 A so if this is the case, it implies that f is onto. I mean, I guess we can assume this. I mean, consider A is 1, 2, 3, 4. And if it's 1 to 1, we have that. So this would be the codomain, and we have that uh, for every, but does it I don't know, maybe I'll need to, assuming A is not an infinite set. Yeah, so if it's yeah, if it's 1 2 3 4, I'm just thinking like F, like if it's 1 to 1, that does that necessarily mean that every element in A has a partner in the natural numbers? I'm getting a notification. Let's see the definition of I think the definition of like onto is that for all A, B in like A, for example, f of x, if f of x is equal to, oh, sorry, f of A is equal to f of B, it implies that A is equal to B. But in that case, this would mean that it's, okay, wait, so if we have, let's, oh, you can't even see what I'm writing. No. Can I highlight this actually? This is a weird program I'm using, by the way. I don't know if I can even, I want to move this. Yeah, I guess I can't really do that. All right, let's be pedantic and let's go through the rabbit hole, okay? Yikes. Okay, I did not plan to spend this much time on this definition. I'm guessing if it's onto, I want to have that something like this. Assuming it's not infinite sets, okay. 1 to 1 function with a finite number. Yeah, maybe I'm not there quite yet. Let's see the definition of 1 to 1. I think Wikipedia has a good one. Set to be injective for all A and B in F. If this is this. Yes, I think I did it correctly. Okay, well, I guess I was wrong. Like, I guess it is for all A and B. Let's see here. Oh, it's maybe. Maybe. Sorry, guys, if I'm very stupid here, but like that's like the process of mathematics, I guess. So that would be. So in the pictures I have here, at least, not necessarily. Yeah, it does not necessarily mean that. all elements in A has a partner in the natural numbers. But we for sure know that natural numbers A to a finite set A because the natural numbers are infinite and a finite set. Ooh. Cannot have in unique elements to map all the natural numbers to. A cannot be finite. Wait. Cannot have enough. I mean, I don't know if I agree with that actually. This is a guy from Google. But this is how we define it, I think, in the book. Yeah, from naturals to A. Oh, so A cannot be finite. But he did give an example here where A was finite. So if A is red, blue, and green, and B, but A. That escalated. I mean, if there does not exist an injective function, you know what? My go-to is just put it in ChatGPT and just say explain this as if I were a 12-year-old. We'll see if this works. All right. This will help. I know my math teacher recommends this. But hopefully you guys can see a little bit what I'm writing as well. I'll try to make it like in the middle of the screen. Bag of objects, and you want to give every object in each bag its own number. Yes. This finite bag. This bag has only a few objects, like 5 or 10 candies. If you try to keep numbering objects forever, you'd eventually run out of objects in the bag. In math terms, a set is called finite if it doesn't have enough objects to match each one to a different natural number forever. Doesn't have enough objects to match each one to a different natural number. Okay. Wait, actually, let me see here. So X is the domain. Oh my god, I did something wrong. I said, okay, this makes now more sense. You see, it works. I swear it works. This is supposed to be n. Wait, let me move this. So for all n, f of a, if f, the function that maps, so if f is actually a function that maps the natural numbers to a, and this is our a, and this is our natural number set. If it's on 1-to-1, we have that, we can pick any, for example, 3 and 5. And if we pick this and then we run it through our function, yeah, if these are equal, yeah, but Mm. Okay, maybe this makes sense. My confusion still arises. If Sitcom, it doesn't have enough objects to match. Like who says that we need that every a has that for every, like, the function maps like every natural number to an a. Like, I mean, if it's not 1-to-1, it doesn't imply that it's like surjective. So if a doesn't have doesn't at least contain the set of natural numbers. No, it's more like if I mean, it's if no, actually, I'm not sure if I can answer that. I don't really know their definition, but I feel like the correct one would be if we have a finite set. I would, if I were the math god that decided to give this definition. I would say that if we have some rest, like if we can eventually map all the natural numbers to all the elements in A, and we have some rest natural numbers. If the first 100 maps to all the elements in A, we have like an infinite number left, like 101 and etc. Then A would be finite. You go live on the other channel? I will, but in like a couple hours. Okay, we'll just read more. Countable bag. This bag could have infinitely many objects, so it never truly ends, but you can still line them up and give each object its own number. Even though it goes on forever, you're still able to hand out numbers to all objects without skipping any. Yes. In that term, a set is countable if you pair each object with a unique counting number. Yes. This is the bijective thing. Countable bag. This bag is so huge that no matter how hard you try, you cannot list all the objects using. Yeah, okay, I think I get this. Because if it's not on 2, then we have it that that we will leave some elements out. That analogy is pretty good. Yeah, I mean, if right. So I think I understand this not countable or uncountable. So huge that no matter how you try, you cannot. For example, there are so many points on the line. If you zoom in really far, you just can't give every single point a number. In math terms, it is uncountable if there is no way to match every single object to a single yes. So in simple words, if your bag has a limited number of items, it's finite. But okay, wait. If f is 1-to-1, it doesn't necessarily. It doesn't mean that each element A is mapped to a natural number, right? this is my confusion. Let's see here. How long have we spent on this? We spent 50 minutes. Wow. All right. Okay, maybe we'll just move on. So we have this. Maybe we'll get its answer and then we'll move on. But anyways, we have this exercise 3.1. We need to show that cardinality of A if there exists an onto map from B to A. So we assume that this is true. Cardinality of this is. I mean, if I'll just write this down. So assume cardinality of A is less than or equal to cardinality of B. I mean, this implies by definition, right? From definition 3.5, right? That, no, wait. Wait a minute. No. Oh, wait. Right. Yeah. So if this is true, then there exists F is on 2. I mean, or no, injective 1-to-1. Right. Let me just see here. Let me see what should say. A function f is called 1-to-1 or injective if whenever you pick two different numbers or objects from the starting set, i.e. the natural numbers, they descend to the different object in A. In other words, yes. So every yes. Does that mean that every element A gets a number? Not necessarily. So f is 1-to-1. We are only making sure that different numbers are mapped to different elements in A. However, this property does not guarantee that all elements of A are hit. An example will illustrate yes. So what's the correct answer? Okay, wait. If this is the case, how can we be certain that A is not? A is finite by definition 3.5. Okay, I see. Oh, well, I think this is possible actually. So, so it's cardinality of A is less than B. We have from A to B, but we need to show that it's F from B to A is onto, which is like the reverse. I think this is very possible. It's actually, I never really thought about this, but hopefully you guys can see this. Okay. Okay, so I guess we'll just write the definition because I think I can do a hand wavy like argument. We know that every element in A is mapped to a unique element in B. Not necessarily that every element in B is mapped to a unique or mapped to an element in A. If we switch the roles, we know that every element in A has a partner in B. We can maybe write both the definitions of onto as well. We can maybe make a parentheses. You can't even see this. We can make a parentheses here saying that. Can I remember the definition? I think I can. For all x in A, there exists. No, I'll do a y. Yeah, I think it's the pre-image, right? For all y in A, there exists an x in B such that f of x is equal to y. So yeah, there exists a preimage x for all y in the codomain. I think this is it. Yeah. Okay. Nice. So this is our goal. We need to show this. This is our goal. Sadly, it's not possible for you to see everything. Maybe you can see it up top. Ooh. Yes, you can actually. Okay, you can see it up top. Let's try not to move it again. Let's see here. From B to A on 2 for all y in A. Okay, cool. So for all x and y in A, if I feel like this can be written in another way. Let's see ChatGPT's answer here. Is this the case how we... Wait, what? Right. This means that if you try to match the natural numbers with different elements in A, you'll eventually run out of elements in A. Wait, it says that it's not one-to-one. Right, so if it's not one-to-one, we can... So that means that if... Yeah, that means that if 3 maps to B, there can also exist another element in the domain that also maps to the same value. If A were infinite, infinite is usually an infinite, and so. If no such one-to-one function exists, it means it's impossible to assign a unique natural number to each element of a putative infinite. What the heck does putative mean? Okay. By the way, is my audio okay? Okay, I think it's okay. There simply aren't enough elements to list out infinitely. I think I understand. Yeah, I think I understand now. Finally. No, I don't think I understand. There simply aren't enough elements to list out infinitely. It would be a way to pick out an infinite list from it. Maybe it makes sense. Oh, that's true. If we cannot define a one-to-one functions from n to a, we can say that a is finite. Yeah, I maybe understand, because then we have to say that the natural numbers have to map to more, like, each natural number has to be have many, or yeah, as the picture, as my picture, you know, as I've drawn it here. I guess I could buy it. But then again, like, that doesn't necessarily mean that that each element in A is. Does that matter? I'm thinking, couldn't it be like, maybe I'm going too much into this. Maybe we'll have to move on. But I don't know. I feel like I want to understand this. Can it not mean that every natural number be mapped to the same element in A? But okay, so if this is an infinite set, this and this is the case, we have that n. The f is not 1 to 1. Is it surjective? Not. No, definitely not. But I guess this is a special case. I guess we wouldn't pick this function. This function is useless. We would avoid picking such a function. But then it would be surjective as well. Like, if we avoid picking such a function, and we always pick a function that like, yeah, I don't know if I think my counterexample still stands. A could be an infinite, like, whatever. But we can still pick a. Let me see. Oh, maybe if there does not exist. There does not exist. Okay, this is different. Do. Every that cannot be a function, right? Every element in A needs a preimage to be a function. No, that's not the case, because this is our codomain. A function. Wait, maybe you're right. No. Like, if this is the real number line, we have that every element in the domain maps to the same element in here. This is what I'm writing. I'm basically writing a y is equal to some constant a, and if this is the real number, then every x here will be mapped to the same element. This is what I'm writing down, basically. At least one preimage, otherwise it's just a relation. For a function, if it were not to be a function, if a would also map to another one, d, then this would not be a function, because it cannot map to two different. The function cannot spit out two different results for a given input. But this is definitely a function. But I think I'm way out of town somehow. I think therefore A must be finite. If A were infinite, then there would always be a way to pick out an infinite list from it. Yes, I think, yeah. If this were infinite, we could, I mean, I guess if it were countably infinite. If it were countably infinite, we could find a function that maps everything one to one. Yes. Meaning that there does exist a one-to-one map, meaning that it's not finite. Okay. So that wouldn't work. I don't know why I'm having such a hard time grasping this. I think your example doesn't rule out the possibility that there exists a one-to-one function. Yeah, I think, yeah, you're correct. I think so. Yeah. Because we can't find a one-to-one function here. Yes. We'll just leave it at that. Jesus. Gotta go. I hope you figured it out. Yes. Thanks for joining, Just Grind. Appreciate it. Yeah, I think we'll just move on. I think I understand the gist of it. Yeah. So in this case, I'm not sure how you would do a formal definition, or like a solution of this. Maybe I can try to do a hand wavy one, you know. I can maybe write. By the way, we're doing. Sad you can't even. Oh, sorry. Let's see if you can see. Everything should be on. We'll maybe delete this. Maybe. I think so. Like this. So this is for question 3.1a for this one here. But yeah, so if f from a to b is 1 to 1, we know I'll do a hand wavy one. We know each a, or I say x in a, maps to unique. Yeah. Elements in, oh, you can't just read that, in B. And we had a definition of surjectivity. We can write i.e. for all, i.e. for all x in A, there exists, we know each x in A maps to a unique element in B. For all x in A, wait, let me just think. Right. Is this true? I think so. There exists a unique y in B. Such that Um, wait, no, no, no. Wait, I need to switch this up because I wanna do like a spin on this definition up top. Um, so I do for each b and for each x and b. Yeah, so whatever we x in b. Wait. Um, oh, I understand. No, I think I'm correct actually. Sorry. Such that f of u is equal to maybe I'll just put this here. I need to figure this camera situation out. Maybe I'll put the camera down here. Is that okay? Is that something that is possible? Is that fine? Oh, let me open the stream up. See how this even looks. We are grinding. Okay, okay, cool. I think it works. Maybe. What do you guys think? I think it works. Okay. Should I move this down? That's maybe better. So I have more space to see what happens. What is happening? Anyways, this will map. Yeah. So for all, so we wanna we wanna show that the function. Maybe I'm writing this very stupidly actually. Maybe. This is very confusing notation even for me. Blah, 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 blah. Okay, we wanna create a one-to-one function. We call this g, and g takes elements from A and gives me elements from B. Okay. So and this needs to be bijective. No. Surjective. So we can pick every element in. Shit. Am I doing this? I think this is the other way around. Yes. I read the wrong thing. Okay. Yes. So for every element in A, we can find. I think we can find a unique one actually. Yeah. We can find a unique element in B. Such that wait. Maybe this is okay. This seems rough. Because if A is 1 to 1, we cannot. I'm thinking maybe we can like do an inverse, but we can't really do that. Uh, um, because like we need to have it bijective if we want to do an inverse, otherwise it won't be good. Right, because if it's not surjective as well, we cannot uh, I'm thinking, yeah, this really puts me to the test of like functions, like how it really works. I mean, I guess I've had like a hand wavy, like I think I understand what 1 to 1 means and stuff, but to be able to decompose it and like restructure it is something I'm not very used to actually. It will ask ChatGPT. I think we'll do that. Kind of stuck. Kind of stuck. If we restrict B, it's not really B, but can we? Maybe we can create a bijection. How can we be sure? Seriously. So this is another way of defining 3.5. No, it's another way we can formulate. It's general language indeed. Indeed, cardinality can be defined as follows. Okay. I wanna move on, honestly. I definitely wanna do that. So we'll see. How would you solve 3.1a, kind sir? I need some ideas. Ideas would be appreciated from people in chat as well. Yes. I feel like also when streaming, you get kind of narrow, like, you don't really have, I don't know, this is like the first stream, so I'm kind of also a little bit stressed about this, so maybe I can't really think that clearly. That's also something to take into account. So there we go. So he says this. Having an injection F from A to B means that every element in A goes to a unique element in B to get a surjection. G, B to A, we reverse this mapping. Yes, we do reverse this mapping, but I guess it is a surjection. I guess it is that simple. I don't need to think about like if it's in inverse or something. Like, I mean, for some reason that is confusing me. Like, I thought it would only be legal like to create, quote unquote legal to create, because this is essentially an inverse, right? G is like an inverse of F, or no? Or reverse. If little b is in big B is in the image of F, send B back to the same A. Send B back to the same A, yes. OG here. For all x in A, there exists a y in B such that g of y is equal to x. If B is not in the image of A, just pick a single default element, A not in A, assuming A is non-empty, and map to B. Yeah, this is interesting because we're actually extending it, like extending the map. Right, and this is important to do for some reason. This construction ensures that every element A is hit by G. So G is surjective. Okay, let's just pick a. There is an injection f from A to B. By definition, that means yes, A is non-empty. Pick an element A not in A, such that such an element exists because A is not empty. Define a function g from B to A. The unique A in B, or little a in big A, with f of little a is equal to B. If B is in the image of F. Versing B has a unique preimage and will be restricted to codomain A. Earlier, every A had a unique mapping to A, so we can conclude that the range and codomain is the same, and hence onto. Oh, that's interesting. Yeah, I guess we can. I'm just wondering, like, we have some B that does not map to any. I guess this doesn't matter. Yeah, I guess it's yes. Case what ChatGPT is saying, that if B is not in the image of F, right. There we go. I think it should be fine. I'm just scrambling, like it's, yeah. We can possibly move on. Hello Bedrock, you doing functions? I'm doing cardinality, and yeah, that involves a bit of function. like knowing a little bit about that, you know. We'll do B. So we know that cardinality. Wait, never mind. So if. Okay, well this is yeah. This should be not the most difficult. Um, uh, Hopefully you can see this. I don't think so actually. Let's move this like this. Okay. If this is true, it implies that cardinality of A is equal to the cardinality of B. All right, let's pick up the pace. Okay, I think with or at least I hope so. I think we've done the tedious first couple stages. In that case, if some elements in B does not have an image, it cannot be a function at all. In that case, we can only consider cardinality of A equal to B. It's not a function at all. I mean, the domain maps to nothing. I guess that's true actually. It needs or is it? I'm just thinking of the wait. Let's see here. Let's just look at the wiki. Yeah, I guess so. But wouldn't it be bijective then? No, not or in this case. Non-injective. What is non-injective? Surjective. A non-surjective function. Non-injective surjective. Ah, okay. It is surjective. Okay. All right. Well, yeah. Seems like you agree, Jemima. So hopefully I'm in the right track. I'm doing with derivative applications. Interesting. What is that for applications? Like physics or? But. Okay, man. I mean, if this is the case here, I guess I can do highlighter. If this is true, by the definition here, we have that there exists a one-to-one function from A to B. Yeah, meaning that every element in A maps to a unique element in B. Here we have that that there exists a function, not necessarily the same, right? That maps every element in B to a unique element in A. And we need to show that if this is the case, we have a function, we have a bijective function. From A to B. Okay, cool. Um, let's see here. Okay. So we just need to show that there exists. I guess we can show there exists f onto and projected. Oh, and projected. There. No. I guess we could do it the other way around because there exists like a unique inverse as well. I don't know if that matters. Yes. Okay. Let's see here. Can I explain the question for once? The question is here, by the way. You can see it here. I'm doing B. So. We can solve using inequalities. That's not the aim. How would you do it with inequalities? Oh, you mean... Oh, well, I don't know if we can use that. Yeah, I guess I see what you're saying. But yeah. I guess it's kind of... yeah. Maybe bad notation, I'm not sure. I think this is basically... actually, it's not bad notation. It's just like we need to first prove that we can do that, and then we can use the inequality, like you say. But yeah. You know, it's quite tricky actually. It seems like intuitive, but I don't know. Like to do it formally, it seems quite tricky. Okay, so we know there exists f. Okay, well, actually, we can use a. I just noticed that. That's 1 to 1. We know there exists a to b. That is 1 to 1. Okay, I think I got this actually. Yeah, we can use a like a crazy bunch, like crazy amount of times. I think so at least. Maybe I'm wrong. Okay. Maybe we can say that this is G. G from B to A. That is onto. We also know that there exists another. We call this F2 maybe. This F1. From B to A. That is 1 to 1. And we know that there exists a G2. That's something. We need a single function that is onto a 1 to 1. Can we merge these functions? Can we merge any of these? We have f1 that is from a to b that is 1 to 1. Wait, we need to show that, yeah, from a to b. And we have g2 that is onto. I think this is like some kind of lemma. Maybe it's the most trivial lemma in the world. if f1 is so if we have one function that is one-to-one and one function that is surjective, does there exist a function that is one-to-one and surjective? Let's see if we can make this more digestible, or I guess more intuitive, for that matter. Let's maybe so we know that there's a function that is one-to-one, meaning that each element may be mapped to a unique. This is not true actually. Wait. So we have that. Wait, let me just see here. We have 5 here, maybe. I guess. Wait, let me. I guess it cannot be. This set cannot be bigger than this. Otherwise, it would be. I don't know if this is the correct way. Okay, let's see. Okay, what does this say? So if it's G2 is surjective, we say that every B can have a partner in A, and if it's one-to-one, we say that every A can have a unique partner in B. It cannot. Yeah, it cannot. I think so as well. Okay, so if it's one-to-one, we have to have that this is less than somehow. But it's very weird because, I mean, I guess we could say it, but I'm not sure if this maps to all cases. This is okay, fine. We have it like this, and in another case we also have it that G2 is so every element here can have a partner here. Is this true in this case? Yes, we can have another one that maybe does that's not correct. Is this possible with this current scenario? I don't think so actually. No, it's not possible. It's not possible. Wait, if it also have many one, then it can be larger set. Wait, so if it's many one, do you mean that I'm not sure if I understand this. When you say many one, do you mean surjective then, or what? That. Oh, what am I doing? Yeah, I'm not sure. It feels like this is programming language, I hear. Are you a programmer or like studying computer science, Jemima? Bruh, I'm not sure, man. I am not sure. How long? Almost for 2 hours, and we've done like 1, 2, or like 4 pages, but not even complete one exercise. This is kind of difficult. I think I'll just maybe ask ChatGPT honestly. An element in B can have more than one preimage. Yeah, yeah. So, um, yeah. So it's not one to one then. I just completed 12th, and now I'm prepping for uni. There's exam. All right, cool. What will you study? Will you study like computer science or something? Mm-mm-mm. Um, yep, but syllabi is just physics, chemistry, and math only. I'm not sure if I understand. Your current syllabus? Or what? Oh, yeah. I think maybe we can. This current one, anyways, back to question. It wouldn't be one to one. Still, it can be on two. Yeah, I'm. I don't know, man. This is getting. I don't know if I'll take a break. Honestly, I'm feeling a bit tired. Like, at least some kind of break. Da-da-da-da. Okay, just a minute. So every element in A. Let's see here. Does it mean they're like duplicates or something in one of the sets? Or maybe not. Do. Okay. I think I'll take a little bit of a break, and then I'll be back. In I don't know how long of a break we'll do. What is time there? It is what is it? 9, just about 8:52. Yeah, so we've been going for around 2 hours. Would recommend discussing with your friends. You'd get it more easier. Or maybe I'll discuss it with ChatGPT. Maybe we can do that, and then we'll like take a break. try to move on to something else. What more questions are there? We're getting into more some Cantor diagonal argument. No, wait. Prove that A and B are, if A and B are countable sets, then a Cartesian product with B must also be countable. So the kind of this is not countable. Prove that A1 is an infinite sequence of infinite sets of at least two elements. Each then is uncountable. Okay, these questions I've actually already done. Set A is such that there exists a one-to-one map, then A is uncountable. Yes, these one-to-one maps are very like not my friends. I want to make them my friends. What did I copy at least? Maybe I'll just copy the whole thing. Or maybe I already did that, right? Maybe. Yeah. Right. How would you solve exercise 3.1? Like this. I feel like I would, if I were to be like study on my own, I would go through these questions faster for some reason. But maybe that's not the case. Maybe with practice, with doing these streams, it'll be better. I guess one can only hope. But we'll get some spicy stuff here at the end, like with Lebesgue measure. But this is very difficult, I feel like. There exists an uncountable subset of R that Lebesgue measure is equal to. Okay, so we have a proposition. Okay. Yeah, let's see if I can get into that. Okay. Okay, let's see what ChatGPT is saying. Keep in mind that in some texts these exercises are stated different, but the version we address here is equivalent to proving that if there exists a surjection G, kernel of A is no larger than kernel of B. Wait, what? This is not what we're trying to do though. Wait, am I? This is not the solution for 3.0. Wait, is this enough to show that it's just an injection between the two? Are these your uni assignments? Yeah, this is basically my uni like course literature that I'm trying to just go through. Surjection B, G from B to A. I want to construct a function that goes in the opposite direction from A to B with the property that if f of A1 is equal to f of A2, then automatically A is equal to 2. I'm not sure if this is not, how is this correct? I don't know, man. 01 mini maybe is better. I think this is wrong. Like, why would we do that? That's not our goal at all. It won't be our goal is to find a bijective function from A to B, right? That is the goal. Granted, I'm not even sure if I completely understand the first one, because we need to extend it somehow. Or I guess we don't need to extend the set, but rather we need to extend the function definition. But I guess that's another thing, right? I need some water as well. Yes. I'll grab some water. I'll be right back. Or he's answering now. Loise's classes Cantor-Bernstein argument that shows that. Ooh, I think I've heard about this. Wait. I think I've heard about this. I think my lecturer said this. Okay, I forgot. So that if there is an injection from A to B, an injection from B to A, there exists a bijection. Restate the problem. We know that there is an injective function. Also know that there is an injection from B to A. Build a graph of A union B. The Cantor-Bernstein proof. Let's search up what is the Cantor. Is this actually via bipartite graph? Schrödinger in set theory, the Schrödinger-Bernstein theorem states that if there exists injective function from A to B, B to A and B, there exists a bijection. So this is the okay, cool. The proof is literally. This is the proof. Oh my gosh. Assumes. Wait. The following proof is attributed to Julius Koenig. Assume that without loss of generality, that A and B are disjoint. For any A and B, for any B and A, we can form a unique two-sided sequence. Of elements that are alternatively in A and B by repeatedly applying F and G inverse to go from A to B and F inverse to go from B and the inverse are understood as partial functions. Oh, it continues. Oh, never mind. Think of each element in A, in big A, and each element in little b in big A as vertices in one big diagram. Draw an arrow edge. Because F is and G are injective, each vertex in A has it at most going out via F. Wait, this is kind of. This is interesting. I'm not used to injective or surjective terms. Rather, I say in simpler terms like onto or many one. I get really confused. Well, yeah, there are many. I just learned many to one today. But yeah, I think yeah, for like surjectivity you can say surjective onto or many to one, right? And then for the one to one you can say it's injective for one to one, right? Ay, ay, ay. Mathematicians like to confuse things. We pair up. Um, I'm thinking if this proof is okay with with infinite sets. Um, but yeah, I need to head out. I'm just gonna grab some water, and I think I need to open my window as well. Right. There you go. I guess we'll get back into it, right? Let's see here. We will get back into it. All right. So this is some proof that is called. This seems like some discrete mathematics. The Schroeder-Bernstein thing. Maybe I wrote it down on my notes during the lecture. I did write it down. Oh, it's with completeness axiom. Yeah, I think. Yeah. I think this is. Yeah. I think my lecturer said you need to know you need to do the you need to use the completeness axiom here. A and B, then bijective with completeness axiom, and this was the Schroeder-Bernstein argument. Let's see what ChatGPT is saying. By the way, goodbye, Jemima. Thanks for joining. Let's see here. Okay, so we know cardinality, this. We want to build a single function h from A to B that is one-to-one onto a bijection. A standard way to visualize the Cantor-Bernstein proof is via bipartite graph. What the frick is this? Think of each element A in big A and each B in big B as vertices in a big one diagram. I think this is what he's talking about. Koenig's definition of a bijection. Is this what he says? Well, he says Koenig. Oh, maybe no. Never mind. We've published it, albeit without proof. Cantor, okay. Koenig's definition of bijection from A to B, from given example in an element in A and B is denoted by a number of and a letter, respectively. The sequence is an A stopper leading to definitions. Wow, this seems very discrete mathematical, you know. Right, so the green arrows are the... Oh, that's way too much. Green arrows are the bijection function h. Shall we try to understand this proof? This seems like a big detour, but this was the question. A standard way to visualize. Think of each element A as vertices in a big one diagram. Draw an arrow from A. I mean, let's try to do this actually. Let's go, people. Let's go. Can you guys see this? Okay, so we have the Cantor-Bernstein proof or theorem. Will I state it? If this to this, one to one, 1, 2, 1, and we have another one called, will we call it G? Yeah, we will call it G. G from, oops, from A to B, no, from B to A. If F from A to B is 1 to 1 and G from B to A is 1 to 1, 1 to 1, it implies there exists an H that is from A to B that is bijective. Bijective. Alright, that's the statement itself. And let's try to do something to convince ourselves that this is true. Think of each element as vertices. So we have A like this. We have B like this. Okay. Draw an arrow from A to f of A. Draw an arrow from B to G of B. Because F and G are injective, each vertex in A must have at least one arrow. Okay, that is, I agree. So we have this. Each vertex, so we know that this is unique. If we go this, we have F that is injective, so each element in F, or we can do it like this, do it like this, do it like this, and like this. And we'll do another color, we'll do like blue. We have another one like this. We cannot have it like this. I mean, I don't know. It must mean that they have the same amount of elements. I'm pretty sure. I'm pretty sure. So yeah. Okay, now we do a red color. Draw an arrow from it. Because F and G are each vertex in A has at most one arrow going out, and each vertex of B has at most one arrow going out. This makes every connected component in the graph look like one of these chains. An infinite path in both directions. One-sided infinite path with a starting vertex that has no arrow entering it. Finite cycle, a loop with edges alternating between A and B. We'll use these pieces components to define the projection. I see. So we can either have that it goes from this. Okay, what do we have? So this goes to there, this goes to there, this goes to there, this goes there, this goes there. So this is a finite loop, right? So it just goes between these guys. I'm guessing this is the same. But I guess you can also have it that, hopefully you can see this, you can have it that we have a point here, we have not, two other sets, this goes to here, and this goes to here. I guess that's another finite set. Ooh, infinite path. I don't know if I understand that, to be fair. Infinite path, so all of them are obviously infinite. Yeah, they have to be infinite. With a starting vertex that has no arrow entering it. With a starting vertex. Oh, so it's just one. I'm not sure if I understand these cases. How to define H from A to B. We pair each. Okay, so we pair each A in A and B in B in the same connected component if the component has a one-sided infinite chain beginning with some A in A naught in A, which is not hit by any arrow from G, I know B in B maps to A not. Let's see here. That is not hit by any arrow from G. I'm not sure if I actually get this. How can it not be hit by an arrow from G? Because blue is G, right? This blue color is G. This guy. And hello Tora, welcome. How's everything going? It's going pretty well, though I am kind of, or I guess it started off very slowly. I feel like I'm getting it to the you know, things are happening, right? If the component has a one-sided infinite chain beginning at somewhere which is not hit by an arrow from G, I know B maps to A. I guess this is this could be true. In this case, right. So if we look at the picture here, no, this is not it. Yeah, this one. Yeah. I'm thinking. Okay, can maybe I'll just ask him. As if I was 12 years old. That is the best prompt to give ChatGPT. Just end it with as if I were 12 years old, or explain it to me as if I were a kid, or imagine you have two groups of people, group A and B, standing on opposite sides of a room. We have arrows going from people in A to people in B. I was getting bored, so decided to join in and study, although wouldn't be able to respond much. That's a neat trick. It is very neat. But you're very much welcome to join, Tora. I was going from. Okay, wait. Group A and B. Yes. Each person in A points to at most one person in B, and each person in B points at most. Yes, that's actually pretty good analogy. When you follow these arrows, you will see that people are gathered into separate chains or loops. I see. I mean, yeah, I do have two loops here, right? I do have two loops. This loop and this loop. A chain that starts at some person in A goes on forever in one direction. A single file line of people where the first person in A has no. Okay, wait. Has no arrow coming in from B. I don't know if can this even happen. This seems like it cannot happen. From that person onward, each person points to someone in the other group. Where the first person in A has no arrows coming in from B. The first person. I mean, maybe. I mean, maybe it can happen. But from both directions, like, wait, let me just think. It means that all elements they have to map to a unique element, but just thinking. I think I need to ask because I'm not sure if if the domain, if all elements in the domain do not map to something in A, is f even a function then? I need to ask. If all elements in the domain do not map to an element in the codomain, can a function still be a function? Is there a rule stating that the domain, I mean, would it even be a domain then? Ooh. What is the definition of a domain? That it has to map to a thing in the codomain? Would that set be defined as a domain? I don't know, man. Hello, Jia. What am I studying? I'm doing. I mean, honestly, it's kind of it's very discrete mathematics. It smells like discrete mathematics. Very much so. It's yeah. I'm doing. It was originally it's chapter 3 on counting and length, about the Cantor set and cardinality of sets, of infinite sets. But exercise B here is some tricky thing that I've maybe I've gone into a rabbit hole, but yeah, I'm just trying to understand this this proof. I mean, the statement is up here. Basically, if we have a function that is onto from a to b, or not onto, 1 to 1, and if we have another function g that is 1 to 1 from b to a, then there exists another function h from a to b that is bijective. Yeah, for somehow we can split it up to different cases. All right, so let's see here. In the usual definition of a function in set theory, every element of the domain must be assigned to exactly one image in the codomain. Formally, a function f from a set x to a set y is a rule that assigns each x in x to one in y. Okay, this makes sense. So yeah, I guess it's good to refresh on the definition of a function, right? Good job on reaching exercise B though. Thank you. All right, I think this is good. Okay, let's see see this again. Well, yeah, it's okay. So if that is the case, let's see here. Oh, that's interesting. That is very interesting. I was thinking that if yeah, so the cardinality has to be the same, and this is the same as saying that there exists a bijective map, and this is what we're proving. Okay. Damn, am I so slow? It feels like I'm so slow. Can't understand it. Lol, I'm still in high school, just here because I couldn't focus. Alright. Yeah. Hopefully some math major joins and just helps me out, you know. I guess I am a math major as well, but somewhat smarter. Okay. Mm. We'll join the study stream later. Alright, see you then, Juja. A line of people that has no first person. If you look left or right, it just keeps going on and on and on. Maybe Wikipedia explains this better. An A stopper, if it stops at an element A, it stops at another way, otherwise call it a doubly infinite. If all elements are distinct or cyclic. How can we not have a... We need to have it that it stops. I don't... Note is half open. Burning hot. Yeah, hopefully you're staying cool. You know. Yes, if you assume the axiom of... you have an axiom of choice. Bro, this seems very unrelated to what I'm doing. Ay. I don't know if I'll just give up on this question because it just doesn't make sense to me. Never give up. Or maybe it's the best thing to do. Because we're not going anywhere. I feels like I'm not really going anywhere with this. Okay. An infinite path in both directions. A one-sided infinite path. Story where says no entering it. It's weird because my lecturer said that you can prove this with the complete axiom, but maybe there is one in this Wikipedia page. Model ordering. Principle exclude middle to draw a conclusion to case analysis. As such, the above proof is not a constructive one. In fact, the constructive set theory, such as intuition set theory, but dispenses with the principle excluding some shading version. In turn, there is no proof for the Cunningham conclusion in this or a weaker constructive theories. Therefore, intuitionists do not accept a statement of Schrödinger theorem. Is there one with completeness? Is there one with the Dedekind? Dedekind complete. Complete, no. Hint. I mean, even if I read the solution, I don't really understand the cases. Like, can you prove the Bernstein? What is it called? Cantor-Bernstein. Bernstein theorem only using using this is what my lecturer said. Do I have my water? I don't even have my water. Alright, I'll grab my water. Alright. Okay. Alright, you remind me to drink some water, noise. Fairly standard proof the counterpart that uses your what your lecturer likely refers to the complete axiom, but is more commonly known as the Zorn lemma or equivalent Hausdorff maximal principle. I don't know what the Zorn lemma is. What is this stuff? This is some, oh my gosh, this is some set theory stuff. Oy, oy, oy. Okay, maybe he didn't say complete this axiom. Maybe he said axiom of choice. That could very well be the case. Because I see axiom of choice everywhere here. Zorn lemma, also known as the Kuratowski-Zorn lemma, is a propositioning set theory. It states that a partially ordered set containing upper bounds for every chain, that is, every totally ordered subset, right, this is partial order set, necessarily contains at least one maximum element. No, but this is basic. This is very, very similar to complete axiom. Okay, I think he said a complete axiom. I'm not sure what a partial order set is. Bruh, this cannot be the way he expected it. See, he expected us to actually solve this problem. This is kind of ridiculous. A reflexive, weak, or non-strict partial order. Commonly referred to as a partial order is a homogeneous relation on a set P that is reflexive and symmetric and transitive. Okay, so it's reflection and symmetric and transitive. But a strict partial order is... But wait, what is a total ordered subset? If it's totally ordered... okay, so it's reflexive, transitive, and anti-symmetric. Yeah, but it's not... what does it say? Strongly connected. It's not total. Okay. Okay, I guess that's okay. Hausdorff max. Okay, this is some set theory, man. These are all partial injections. We order them by extension. We learn new things every day, but if it is outrageous, then it's crazy. Like, you have to research so much to have one question. Damn, I guess I'll have to do that. If I'll have to do that, I'll be cooked. I mean, this is an optional question. Granted, it is optional, it says here, but... And he did say that you don't have to do it. But even if it's optional, like, give us some hint. Okay, I'm a baby now. I'm complaining. Okay, let's see. We order them by extension. One partial injection is bigger than another if it agrees on the whole domain. We use the completeness. There is a maximal partial injection in that set. We then use the other given injection to show that this maximal partial injection must also be want to be... Wait, what? The respective given injection, we order them by extension. One partial injection is bigger than another if it agrees on the old domain and has strictly larger domain. To show that there exists a maximal partial injection in that set, we then use the other given injection to show that this maximal partial injection must actually be onto. Is there a video online? There's some smart guys who's done this. You guys can't hear this.
So let's get started. So here's a statement of the Cantor-Schroeder-Bernstein theorem, the insight on the proof. So this example is from the mathematician David Hilbert. It's a thought experiment that he came up with to illustrate some of the counterintuitive or surprising properties of infinite sets. So Hilbert's hotel is a hotel that has infinitely many rooms, numbered 1, 2, 3, and so on. In other words, these rooms are numbered by the positive integers. And we assume that each room is occupied by exactly one guest. So the question is, what happens if a new guest shows up at the hotel and wants a room? Can we accommodate the guest in the same way? Meaning, can we accommodate the new guest in such a way that all of the guests, old and new, are occupying exactly one room? So surprisingly, the answer is yes, we can, and here's how we do it. To accommodate the new guest, we move the guest that's currently in room n to room n plus 1. And we do that simultaneously for all guests.
Oh, is this what we're doing? I'm not sure if you can hear this well. Probably not.
And then after that's done, we put the new guest in the recently vacated room number 1. Once that's done, we have accommodated all of the guests, both old and new. So this is somewhat surprising and a little counterintuitive when you first see it, but we can actually do much more than this. Suppose that countably infinitely many new guests arrive and want rooms. Can we accommodate all of these new guests? Again, surprisingly, the answer is yes. The way we do it in this case is we move the guest that's currently in room n to room 2n, and then put all of the new guests in rooms 2n.
It's not that clear, yeah.
So what this means is
Okay.
we're taking the guests currently in room 1, moving them to room 2, the guests currently in room 2.
I have desktop audio. Maybe I can. System? Maybe?
Moving them to room
2. Oh, I think I know. Browser?
4, and so on. In other words, moving all of the existing guests into the even numbered rooms, and then putting the new guests into the recently vacated odd numbered rooms. So the new guest number 1 goes into room 1, new guest number 2 goes into room 3, and so on.
I think you can hear the double audio as well. It's not the best, right? Oh, you can do it with the Hilbert room.
These examples give us enough of an idea to prove the Cantor-Schroeder-Bernstein theorem. So let's take a look at that. So in order to draw the connection between the Hilbert's hotel example and the Cantor-Schroeder-Bernstein theorem, I'm going to draw the two sets A and B in the theorem as lines. So the points in the sets are the points on the lines. And I'm going to draw an arrow indicating the mapping G from B into A. So we're going to envision that the points in A are guests and the points in B are rooms in a hotel. And we're going to envision that G is telling us the guest that's currently occupying a given room. So
Alright, I'll see you, cookies. Good luck with your biology.
B are mapped into this part of A on the right. And this part of A on the left is not mapped into. So that means that these are guests that don't currently have rooms. Recall that what we're trying to do is construct a bijection from A to B. So essentially what we're trying to do is accommodate all of the guests, both the guests that currently have rooms and the ones that don't currently have rooms, and find them all rooms. We need that each guest is mapped to a distinct
Okay, so G maps, I guess he maps all of these guys into this, but
So we can use F to indicate the rooms to
maybe
which
just this
we would
point.
like to map these guests. Of course, we can't just shove them in those rooms because we already have guests occupying those rooms. And we can see which guests those are by applying G to that image set of A naught under F. So when we apply G, we see this set A1, which is defined to be G of F of A naught. We see that this set A1 is the set of guests currently occupying the rooms where we would like to put the people in A naught. So in order to accommodate the guests in A naught, we're going to shift or displace the guests in A1 down to new rooms using F. So this is very similar to the Hilbert's Hotel example where we were moving a guest down by one room. Except here, we are moving sets of guests, possibly infinitely many guests, using F. And we keep repeating this infinitely many times. So A naught gets mapped by F, that displaces A1, which will then displace another set of guests, and so on, infinitely many times. So let's make this formal. We let A naught be A times G of E.
Honestly, I don't think this is worth my time, honestly. This is some fairly... I don't know, just I don't seem to understand this. Moving on to some fancy theorems. Yeah, this... Basically, we're basically at the same stage we were when you were here last time. I mean, we're still in B here. Apparently, this statement has some fancy name called Cantor-Bernstein theorem, and I can't seem to make this make sense. Yeah. I'm not sure how he wanted us to prove this, but it seems like a lot of work, not gonna lie. Maybe I'll just end the stream here, grab some early lunch, and then we'll start with the study with me stream. Yeah, I think maybe that would be the good thing to do. So yeah. Oops, that's fine. Only got about 200 words, but I compiled some readings. Oh yeah, just completed an annual report writing session. The start is so hard. Yeah. Yes. But or we'll just move on. We'll just. I think we'll just move on. I want to at least do some do some questions. Yeah. I want to do something, right? All right. So we have question 3.2. This is a common retort to Cantor's diagonal argument. So this is, I think he introduces now like diagonal, like a very like rough proof of proving that R is not countable. Yeah, I mean, it's a proof by contradiction, and it's fairly like the idea is fairly simple. So I think I'll just skip this because yeah, it's fairly, yeah, it's not that difficult, I would say. Power through, let's go. Yeah, we can see how far we'll go. So now we have 3.3a. All right, maybe I'll do that like during some other time. Maybe I'll ask my professor as well how he wanted us to do it, because yeah, it's fairly deep, I would say. If A and B are countable sets, then A cross B must also be countable. Yes, I think I did this, like if I have A1 and um, mm, so we want to prove that um, right, so let's see here. Um, let's see here. Mm, this is actually quite because we did do the rational argument, but like how I did it before. Um, mm, I mean, I guess you could do this, but it feels a bit unrigorous, honestly. I feel a bit, yeah. I mean, if we list all the elements here, and then all the elements here, where little b and little a are elements in A and B, then we can create a bijection by just by going like this, and this would be our bijection. So this would be the 0th element, the 1st element, the 3rd element, or the 2nd element, and this is the 3rd, and 4th, and 5th, and so on. Okay. But then again, like let's see here. Let's see here. Okay, so now we have A1 to AN countable sets, then A1 to AN are also countable. Yes, so okay, since C is that if A1 to A2 to dot 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 is an infinite sequence of finite sets of at least 2 elements each. Yes. Let's see here. I think I had very similar question on the seminar sheet. This was a seminar we did on Monday, I think. Yeah, so this is very similar. I think I'll just skip this because I've already done this. But if it's that A is such that there exists a one-to-one map, then A is uncountable. Okay, this is quite an interesting one. If it's that A is such that there exists a one-to-one map, then A is uncountable. To the real numbers. Okay, this is fairly interesting actually. So we have A and then we have the set R. And like from the definition before, if oh wait, let's see here. We have it that wait, let's see the definition here. So if there exists an one-to-one one-to-one function from A to B, We know the cardinality of A is less than the cardinality. In this case, B is R. Okay. But this doesn't really, this is just notation for the same thing. And we need to show that it is uncountable, i.e. that it is not surjective. It's uncountable. There does not exist an F. Okay, so I need to show there does not. How do you do there does not? I don't know. There does not. Can you see this? Yeah. Exist. Okay. Okay, so all elements of A is mapped to unique elements in R. Okay. Maybe we can do the with the contradiction of this. So prove that if the set if there exists a one-to-one map, then there does there does exist a surjective mapping Any ideas? I was just chilling. I gotta get back into writing. Alright, yes, good luck with that, James Grind. Yes. Maybe I'll just end the stream here. I feel like it would be a good thing. But I think I'm just gonna end it here, to be fair. I think it was a nice test. Maybe I'll change some formatting and maybe prepare a bit before the streams. I don't know. But yeah, I'll be starting the Start With Me stream. I don't think I'll yeah. I've gone for 3 hours. I feel like that is enough. I didn't want to go the entire day. But yeah, it was nice having you guys here. I'll do one tomorrow. And yeah, hopefully go better then. But yeah, I'm very happy I at least tried doing this kind of stream. And yeah, hopefully we can get more people in next time. We were very low, but yeah, it was cool. Take a break with healthy lunch. Yes, I will. But yeah, I'll start the Start With Me stream in maybe like 1 hour or even less, to be fair. I still have a lot to do, and I didn't want to do mathematics all day as well, so it's like, yeah, it's more like a productivity thing. I have other topics that I want to cover. I honestly thought I would be able to do this a lot quicker, but apparently it's a bit more difficult maybe to do it while streaming, versus not doing it while you're streaming. You ask your math friends if you want to join. Maybe I can do that. But I wanted to pick up pick up people on its own. Yeah, I mean that's obviously not. You can't expect that for the first stream. But yeah, it was nice testing it out, and yeah, I'll see you guys in like 45 minutes or 1 hour when I'll start the